In this video I'm going to describe how I use this real 6502 CPU over here to debug a problem I had on my emulated CPU which is running on this Raspberry Pi over here. I'll go through the actual circuit and go over the circuit diagram to describe how the circuit works. Then I'll go into the actual emulator and show the problem I was having with the emulator, what wasn't actually running correctly. Then after that I'll go over the actual real CPU running on my Raspberry Pi, the same code and actually working. And then I'll go over to debug output information that I have. So I produced debug output for the real 6502 and for the emulated 6502 and show how I've found the point in the code where the two differed on what they were doing. And then I'll go over how I actually resolved the issue on the emulator code for the CPU. And then I'll actually show the resolved code where I've actually fixed the problem on the emulator and show that working properly. And then finally I'll go over the source code to show how I can switch between the real CPU running on my emulator and the emulated CPU running on my emulator. So this is the circuit for interfacing between the 6502 and the Raspberry Pi. Now I've used a serial interface between the 6502 and the Raspberry Pi. There is actually enough GPIO pins on the Raspberry Pi to do parallel interfacing, and that would have actually been a lot quicker, but because I had these serial chips and I haven't used these yet, I wanted to use these to try them out. So I've got the CPU over here, and the things that need to be interfaced are, because I'm doing it in serial chips, so they have 8 bits per chip. So I'm doing the low address 8 bits, I'm doing the high address 8 bits on another chip, and I'm doing the data bus on another chip. So that's 3 chips. And because the data bus is bidirectional, I've actually got another chip to do the data bus in the opposite direction as well. So, and any control signals, like some of these control signals over here, I actually need to interface as well, but they're just going straight to GPIO pins as they are. So just taking a look at the low 8 bits of the address bus. So they all come out in this direction only, so they come from the CPU into the Raspberry Pi. And these chips I'm using here are shift registers, where you can load the input bits into the shift register, and then you can use the clock signals to latch the input signals in and shift the data out and into the Raspberry Pi. And when the data comes out of the shift register, it comes out of this pin 9 here. So I've got 3 of these pin 9s for the high address byte, the low address byte on the data bus, which then get clocked into the Raspberry Pi on individual pins. So if I scroll up a bit here, you can see this is the data bus part that I'm using. So I'm using, to read the data bus, I'm using another one of these chips which I used for the address bus, but to actually write the from the Raspberry Pi into the data bus, I'm using one of these, which is a different shift register, which is 74595, and I can go in the opposite direction here, so I can actually shift bits into the chip from the Raspberry Pi. And then I've got output enable control, so I can switch off the outputs for when I don't want to actually send data to the data bus, because the data bus is bidirectional bus. So when the actual 6502 is right into the CPU, right into the Raspberry Pi, I actually want to turn this chip off, so it's not arguing with what's actually coming out of the 6502. But when the 6502 actually wants to read some information, then I can turn this chip on, and the information will come out of these pins here. Now, as a safety measure, I've got these 10k resistors here. That's just to limit current, because just in case, and they're probably, when I'm developing code and maybe even at other times, there could be, this chip could be on when the actual CPU is trying to actually output data as well, and so they could be in conflict, and these 10k resistors limit that to something like 0.5 milliamp of draw from the actual CPU itself, so it shouldn't affect the actual operation of the CPU, shouldn't actually damage it. And then if I come across here a bit, so any signals come in from the Raspberry Pi and into the shift registers, I can just read those straight into the shift registers, because the shift registers TTL and the Raspberry Pi is outputting 3 volt 3 signals. the actual 5 volts of the TTL, the 3.3 actually complies to those levels, and so actually I can just send those straight into the chips without having to worry about damage. But any signals come in the opposite way, I'm having to go through these potential dividers. So I've got 5 signals which I'm reading from there. Things like I think it's a non-maskable interrupt, things like that. So that they come out here, and it gets potentially divided down to 3.3 volts from the 5 volts, and then it can safely go into the Raspberry Pi without damaging the Raspberry Pi. The only other part of the circuit I've got is up here. I've also included, because my emulators sometimes output sound, so I've included the circuit to actually output BP sound, like for the ZX Spectrum and also for the Apple II. So to demonstrate the actual error I'm getting in my emulator before I actually fix the problem, if I start up my Apple II emulator, so this is using the early ROMs from the Apple II, and to go into basic, you have to go Control B and then hit enter, and it brings you up to a basic prompt. Now if I type in 10 print, you can hear it makes a noise and it just hangs there. So that's the error I'm actually getting. So in the makefile for my emulator project, at the very top I've got these definitions where I can actually change options for the actual emulator itself. I've added this option in here where I can actually change it so that instead of compiling for the emulated CPU, I can compile so that it uses the real CPU over the GPIO pins. So if I save this, and what I'll do is I'll build an actual build of it using the real CPU. Okay, so I've built a version of the emulator which is actually using the real CPU rather than the emulated CPU. So if I run this emulation, and it actually runs a bit slower because I'm going through the actual GPIO pins to actually send and receive data to this CPU. So you can hear the beeper clicking rather than buzzing. And so I've got a prompt. It runs fast enough that I can actually type in keystrokes and it'll work. So if I go Control B and enter, I just have to wait a couple of seconds and it'll go into basic prompt. Okay, so now I'll do exactly the same as I did in the emulated CPU and type the same line in. But now when I hit enter, it comes back at the actual basic prompt, so it's actually accepted that rather than hanging and sending information to the beeper, it actually accepts that line, and I can actually list it and I can run it as well, and it doesn't hang at all. So I know that there is an error in my emulated code because it actually runs on the real CPU. So when I run my emulator, I can run it in debug mode and produce an output into a file of all the instructions which are being executed. And so I've done that with my running the real CPU, and also I've done it again running the emulated CPU, producing that bug which I've just demonstrated. So on the screen here I've got the emulated debug output on the left and the real debug output on the right. Now just running a few seconds of emulation and having debug output produces a file which is a few megabytes in size because it runs so many instructions per second. But going through the file, all I have to do is find out where the actual emulated debug output starts to differ from the real debug output, and so I've just put a little bookmark in these debug files when I found it, just so I could get back to this position and I can go through it on this video. So up here you can see it does BNER, it does BNER over here, it does bit Z0 page, bit 0 page here, and it does BPLR, BPLR, BPLR again, and BPLR again. But then it does something different. It does storage 0 page here, and it does BMIR here. So something went wrong at this point here. And as this is the emulated one on the left, you can tell it's the one on the right is the real CPU, because I'm not bringing back any information about the actual registers. So you don't get register information over there, but on the emulators one I can actually bring back the information about the registers which are being emulated. So something wrong happened, and it's gone to a different place in memory. But if you look over here, so this is the address it was at, E365, and again on the real CPU it's E365 address. But next it goes to E2E5 on the emulated, and it goes to E366 on the real one. So the jump has incorrectly happened. So what I can do now is I can actually go to my source code and look up this instruction and see what's happening in this instruction, which is incorrect in my source code. Bearing in mind that it's actually going to an address which is backwards here and it's forwards here. So this is the code for my emulated 6502 CPU, and I'm at the instruction BPL register here. So this is the instruction which is misbehaving, and what it does is if it meets the condition which the branch is at, which is if it's positive, so not negative. So I'm checking the negative flag, and I've got an inverter there to say if it's positive, it will actually do the branch instruction. If it doesn't comply to this, and then it will just go on to the next instruction. But here I'm changing the program counter, and I'm going by an offset of which is in the next byte in memory, but it's not going in the right direction for this particular one. And I found out that actually what I'm doing wrong here is because I'm casting it to a assigned value, which needs to be done because if it's greater than 128 it goes forward, and if it's less than 128 as a signed value it goes backwards. So it needs to be able to do that. But the actual signed casting I'm doing here, it actually should be not on that side of the bracket, it should be on this side of the bracket. So I'm only changing this part to be assigned, and then this +2 has to be a positive +2 because it goes from the end of the instruction. So that's where the error was. And if I actually build this now with this corrected, and I've gone through, so this bearing in mind that this isn't the only place where I do relative branching, there's other branch instructions. So I've gone through all of the code, I've corrected all of the code where I've got relative branching so that this is done in the same way, so the cast is on that side of the bracket. So I'll fix that code, so I'll compile this and then I'll demonstrate it actually working now. So I've recompiled the emulator with the fix to the code. So this is the emulated version. Now if I go Control B, go into basic and 10 print, and that now accepts the line like it did with the real CPU. So that's the bug is now fixed, and it's been fixed because I can do comparisons between the debug output of the emulated CPU and the debug output of the real CPU. So this is the source code for actually interfacing the real CPU into my emulator, and so the actual code itself has the same. I have to provide the same functions in the real CPU as I do in the emulated CPU. That way I can just remove the emulated CPU and replace the real CPU code in its place, and it will just run like it would normally as if it was the emulated CPU. So at the top I've got this, which is in the make file where I define whether it's the real CPU or the emulated CPU, and it just excludes the code if it's the emulated CPU in this case, or if it's in the emulated code it excludes the code if it's in the real CPU. So that's the way I use the make file to decide whether or not I'm using the real or emulated CPU. And at the top of this code I've just got, as I was working out how to do the circuit, I just laid out comments on how the actual chips are actually wired and where they get allocated to on the actual Raspberry Pi of the pins. And I've sent off for some PCBs to be manufactured because it's a bit of a rat's nest on the actual breadboard circuit. And hopefully it should run a bit quicker as well when it's on the real circuit board rather than having all these long wires. So a lot of this code you might find has to be here because it has to comply with the ability to do debug, and I want debug output anyway, even if it doesn't. At the minute it won't output the actual register values, although I could I could query the CPU and get the register value back. It would run even slower, but that would be an option if I needed to do that as part of a debug session. But the code and the variables should all be the same so that it just fits in the code. Here I'm using an array of the actual mnemonics for the instructions, so I can just look up the instructions and actually output them into the debug. So in the actual emulated CPU, if I go down halfway down the code, you see here I've actually transferred into a mnemonic string, the actual mnemonic as it executes the actual instruction which is being executed. So I can't do that in the real CPU. I have to have a table where when I read back the instruction which is being executed by the CPU, I can actually just look it up in this table then, and then I can actually get the same debug output as I would as if I was emulating the CPU. So these are just necessary, these functions in order to comply with the interface with the emulator. And I do the initialization. I have to set up the pins on the Raspberry Pi to be input or output as is required. And you have to do, when you're using C and you're interfacing with the GPIO pins, you have to do open up memory and actually go to actual the GPIO interface itself and configure it manually. There may be a library for that now. I'm just used to doing this from the early days of the Raspberry Pi, and so I just use the same code now for doing that. Even I haven't looked to see if there's a library to do it simpler. So this is all just standard stuff. You'll find the very similar code in the actual emulator CPU to this stuff. I had to do a special yield code in order not to actually flip the GPIO pins too fast, because if you flip them too fast then the CPU can't keep up. And I think a lot of that's because of the long wires, and so I think they don't actually flip very fast as they could do. And then this is the actual CPU where it would be the emulator, but I'm doing it the real thing in this particular case. And so I need to actually do, so this is the reset part of the emulation, as it would be emulation, but I'm actually having to actually set the reset pin low on the GPIO, and then I'm doing 10 clock cycles on the GPIO pin, and then I'm bringing the reset back high again. So I'm actually doing a physical reset on the actual real CPU there. And then this is where I would go into the actual each cycle of the actual emulation of the CPU, but in this case again I'm having to do it on the GPIO pins for real. So this is just some stuff I've had to do in order to get the debug stuff still working, but commenting out bits that actually I don't actually want to do on the real CPU. And then this is where I actually do an instruction. So I take the CPU clock low, I disable the data output so that I'm not having conflict with the CPU on whether or not the Raspberry Pi is sending data to the CPU or the CPU is providing data to the Raspberry Pi. I read the status flag. So the sync flag tells me when an instruction is started, which is a really handy flag to have on the CPU itself. On the Z80 there's a similar flag, the M1 flag, which tells you when the first byte of an instruction is occurring. I'm also looking as to whether or not the CPU is doing a read or a write, and they're the only status flags that I really need to look at. Then I load into the shift register, so the values, so I can actually clock, because I've got 3 shift registers. I've got address low, address high, and data bus. I can actually use 8 clock cycles to clock the bits into each of those simultaneously. So if you go back to the circuit diagram, you'll see that they're all linked together. So the latch in and the clock in is all linked together. So when it clocks all of the chips. So here I'm actually latching the values into the shift registers from the CPU, and then I go through 8 bits. And I build up the data bus value from reading this GPIO pin, and I build up the address value from reading 2 GPIO pins. So I'm reading this one, and then at the top here I'm reading this one, but shifting it 8 bits more to the left than the first one. So that's the high byte, and then the one on the left here is the low byte that I'm reading. So I'm building up the address in one instruction there, and then I clock the shift register so that it clocks to the next bit, and it goes around the loop and builds up all the 8 bits for the data bus, address bus low and address bus high. At that point I know what the CPU wants to do, so I know the address that it's executing, and I also know the data byte which it wants to actually execute if it's part of the sync pulse at the same time, or if it's not part of the sync pulse and it's additional data. And what I can do is if the CPU read flag is set, then it means it wants information from the Raspberry Pi into the 6502 CPU, and so I do the data in the opposite direction here, and this is where I'm sending data to the 74595 chip. So this is sending it in the opposite direction, but doing exactly the same as the shifting it in the opposite direction as you saw above. Then I latch the data into the into the output buffer of the data register which I'm sending to the 6502, and I set the output to be enabled so that the 6502 can actually read the data. And then I do a clock cycle, finish the clock cycle of the 6502, and so it keeps going around in that loop. And if it's not read flag, then it wants to write data, and so this is where it does the writing of the data, and it latches stuff, the information. It sets the data coming back from the 6502 into the Raspberry Pi, where the Raspberry Pi I need to put it into the emulated memory, because the memory is still being emulated. And that's it, and then it just goes around cycle after cycle, sending and receiving data from the 6502.